Dear students, greetings for the day. We know that electric charges are two types, positive charge and negative charge. The flow of charge is called current. So the flow of currents is known as electricity. Either positive or negative charges flow represents the electricity. So conventional current represents the flows from the positive pole of the battery side, whereas actually electrons move from negative pole of the battery to the positive pole of the battery direction. That is electric current. But electronic current symbolically, conventional current is represented that flowing from the positive pole of the battery in the circuit diagram. So this charge is at a higher level is known as said to be at higher potential, and when it is at a lower level it is said to be at lower potential. So like water flows from higher level to lower level, similarly charge also flows from higher potential to lower potential when connected by wire. So from one end of the wire or conductor to the other end of the conductor, from higher then current flows from charge flows from higher potential side to lower potential side. So this potential difference is measured in terms of volts, and the flow of electrons is known as electric current, and it is represented by I. It is measured in terms of amperes. So at constant temperature, the electric current flowing through the conductor is directly proportional to the potential difference. This is known as Ohm's law. So Ohm's law states that at constant temperature, the current flowing through the conductor is directly proportional to the potential difference. Therefore, according to Ohm's law, I is proportional to V, or I is equal to some proportionality constant into or V equal to IR. This equation is known as Ohm's law. Here the proportionality constant R proportionality constant R is known as electric resistance. when a person is climbing the cycle, then it acts like a cycle brakes. So electric resistance offers the resistive force to the flow of electrons in the circuit. It is measured in terms of ohms. Oh, in a silent. It's a silent. Therefore, electric resistance is the force of resistance offered by the material for the flow of electrons in the circuit. And this resistance changes with temperature. So it is known as temperature dependence of resistance. So with change in temperature, resistance of the material changes. In case of insulators and or bad conductors and semiconductors, resistance of the materials decreases with increase in temperature. Whereas in the case of metals, temperature, with the increase in temperature, resistance increases. Resistance of the metals increases with the rise in temperature. This is known as temperature dependence of resistance. Now, we know how the resistance of the material changes with increase in temperature. Let resistance of the metal resistance of the material at 0 degrees B, R0 and RT at T degrees centigrade. Then change in resistance RT minus R0 is directly proportional to the temperature at 0 degrees centigrade and increase in temperature T minus 0, that is T. So by combining these two, so here RT minus R0 is equal to some alpha into a proportionality constant. Alpha is called temperature coefficient of the material. Proportionality constant, here alpha is called as temperature coefficient of the material. and this temperature coefficient is positive in the case of alpha is equal to RT minus R0 by R0 T. So this alpha is positive in the case of metals, and in the case of insulators and semiconductors, alpha value is negative. So it is called negative temperature coefficient in the case of insulators and semiconductors. And in the case of metals, alpha is said to be positive, that is positive temperature coefficient. Alpha is said to be positive temperature coefficient for metals, and the negative temperature coefficient for insulators and semiconductors it has a negative value. Now the effective resistance when resistances are connected in a series. So when three resistances connected in series, then their effective resistance value is Re is equal to R1 plus R2 plus R3. If there are two resistances, then Re is equal to R1 plus R2. And when they are connected in parallel combination, then effective resistance value is equal to 1 by R effective is equal to 1 by R1 plus 1 by R2 plus, if there is third resistance, then 1 by R3 plus 1 by R3. These are the effective resistances. Formulas are resultant resistance. Now we shall again recapitulate the Kirchhoff's laws. Kirchhoff's first law is called current law. Kirchhoff's second law is also called as Kirchhoff's voltage law. Kirchhoff's current law. It is also called KCL. So according to Kirchhoff's first law, the algebraic sum of the currents meeting at a junction is 0, or the sum of the currents flowing towards the junction is equal to the sum of the currents leaving the junction. So according to KCL, Kirchhoff's current law, the algebraic sum of the currents meeting at a junction in a network is 0, or let this be junction J, and let there are two currents flowing, I1 I2. the sum of the currents flowing towards the junction is equal to the sum of the currents leaving the junction. Therefore, here I1, I2 are flowing towards the junction O. Currents leaving the junction are I3 plus I4 plus I5 are according to first statement, when I1, I2 are taken as positive and the currents leaving the junction are I3, I4, I5 are taken as negative. Then I1 plus I2 minus I3 minus I4 minus I5 equal to 0 according to first statement. Algebraic sum is equal to 0. So when currents flowing towards the junction I1, I2 are equal to the sum of currents leaving the junction, that is I3, I4 and I5. When we write in one side, then algebraic sum of all the currents is equal to 0 according to first statement. Now second law is Kirchhoff's second law is voltage law. KVL, this is called second law. According to KVL, second law, the algebraic sum of the currents EMFs. EMFs means electromotive force, which is like battery, which drives the electrons to flow through the circuit. It is also, EMF is also measured in terms of volts. EMFs and potential drops, that is products of currents and resistances across the resistances. In a closed network, the sum of EMFs is equal to sum of the products of currents and resistances. Therefore, if we consider two resistances, A1 R2, potential drop across R2 is V equal to I2 R2. Then battery voltage EMF V1, then I1 R1 plus I2 R2 is equal to VR I1 R1 plus I2 R2 according to first statement, that is I2 R2 minus V equal to 0, V equal to IR, which is due to battery, V equal to IR, the resistance of the battery will R. So now we shall use these Kirchhoff's laws in deriving the balancing condition of the Wheatstone bridge. As the name indicates, here the resistances which are connected in the circuit are forms the bridge. So this seems to be like bridge. So it is called Wheatstone bridge. That's designed is to be Wheatstone. Derive the balancing condition for this Wheatstone bridge. So in this Wheatstone bridge, there are 4 resistances PQRS which are connected as shown in the figure. Let this be junction A. Let this be B. Let this be C. Let this be D. So here the A and C are connected between the terminals of the battery. Like this. Let this be positive, negative. So current is flowing in this direction, and this I splits up here at A as I1 in this one and I2 in this resistance Q, I2Q, and let this be R, and let the current flowing through this be I4, let this resistance be S. Here I resistance Q, galvanometer, this current is flowing as IG, resistance is capital G. So this circuit diagram is known as Wheatstone bridge. In this Wheatstone bridge, there are 4 resistances P, Q, R and S are arranged like this, connected like this, and they are connected to the battery between A and C. So this seems to be like a bridge. One is ABC and another is ADC. So this is called Wheatstone bridge circuit diagram. And now we shall derive the balancing condition of this Wheatstone bridge. So when the resistances PQRS are adjusted such that the current flowing through the galvanometer is 0, Ig equal to 0, then the bridge is said to be balanced. That is, upward flowing is equal to the downward flowing. then at that time, since Ig equal to 0, I1 equal to I3, I2 equal to I4. So in this circuit diagram, applying in this circuit, applying Kirchhoff's first law, Kirchhoff's current law at junctions B and D. What happens? So junction B is this one. So up, incoming currents is I1, outgoing Ig and IR. Therefore, I1 is equal to Ig current flowing through the galvanometer is let it be Ig plus I3. And at D, I2 plus Ig is equal to I4. Let this be equation 2. Now applying Kirchhoff's voltage law to the closed loops, applying Kirchhoff's second law, Kirchhoff's voltage law to closed loops A, B, D, A, and another one B, C, D, B, B, C, D, B. Then we get A to B, I1P, I1P plus Ig into galvanometer resistance is equal to minus I2Q is equal to 0, and let this be equation 3. And B, C, D, B, close this circuit. First one this one, second one this one. So B to C, I3R, C to D minus I4S minus this direction, B, D to B minus Ig, capital H equal 0. Let this be fourth equation. When the bridge is balanced by adjusting the resistances PQRS properly, then Ig, current flowing through the galvanometer, becomes 0. Ig equal to 0. Then bridge is said to be balanced. So when the bridge is balanced, Ig equal to 0, then equation 1 becomes so when the bridge is balanced, Ig equal to 0. Substituting the value of Ig equal to 0 in all the 4 equations, then they become, then one becomes, what happens, I1 equal to, then it becomes I1, I3 becomes I1 equal to I3. Let this be better, and let this be fifth one, and second one becomes second one at T. I2 plus Ig equal to I4 becomes I2 is equal to I4. Let this be 6. Now these two also becomes, and equation 3 if Ig is 0, this part is 0. Therefore I1p equal to I2q. And equation 3 becomes I1p equal to I2q. Let this be 5, 6, 7. And equation 4 becomes when Ig is 0, this Ig into G is 0. And this I3R minus I4 is equal to 0. I3R is equal to I4S. And fourth becomes, and equation 4 becomes I3R equal to I4S. Let this be 8th one. So dividing 7 with 8, equation 7 with 8, with equation 8, then we obtain I1p equal to I1p by I3R and I2q by I4S. Since I1 is equal to, from equation 5, I1 is equal to I3. Therefore, this I1 is equal to I3 and this I2 is equal to I4. Then what happens? I3 by I3 gets cancelled. Then P by R is equal to I2 is equal to, from the sixth, I4. Therefore, I4 gets cancelled. This is equal to Q by S. R. This may be written one order. P by Q is equal to R by S. This is known as balancing condition of the Wheatstone bridge. Therefore, the ratio of P and Q is equal to the ratio of R and S. Then bridge is balanced and Ig becomes 0. Current flowing through the galvanometer becomes 0. When the ratio of P by Q is equal to R by S, then current flowing through the galvanometer is 0 and the bridge is said to be balanced. So the balancing condition of the Wheatstone bridge is P by Q equal to R by S. That is the ratio of the first two resistances P and Q. P by Q is equal to R by S. Then the bridge is balanced. This equation is known as P by Q is equal to R by S is known as balancing condition of the Wheatstone bridge. So here, based on this balancing condition, there are few problems also in exam. Here we go. And basing on this Wheatstone bridge, meter bridge is designed to find the unknown resistance value and also to find the specific resistance of the given wire. So now we shall discuss about the Wheatstone bridge. Before going to that, once again we discuss the derivation of balancing condition of Wheatstone bridge. So here first resistance are arranged like a bridge as shown in this diagram, and Kirchhoff's first law is applied to the junctions B and D in first part. So currents flowing through towards B is I1 only, I1, and going out is IG, current flowing through this galvanometer, and also I3. So I1 is equal to I3 plus IG. When IG is 0, when IG becomes 0, then I1 is equal to I3 when bridge is balanced. Similarly, when we consider the junction D, the currents flowing through the junction is I2 and IG. So here I2 plus IG is equal to I4, outgoing current, the current leaving from the D. I2. When the bridge is balanced, IG is equal to 0, therefore I2 is equal to I4. And the equation 3 becomes, that is when Kirchhoff's voltage law applied to this closed loop, ABDA, this closed loop, this triangle, first half triangle. So ABDA, then that equation is I1P plus IGG minus I2Q is equal to 0, or when bridge is balanced, IG is equal to 0. Therefore, the third equation becomes I1P equal to I2Q. Similarly, fourth equation is obtained when applying the Kirchhoff's voltage law to this second half part, that is closed loop BCDB. So from according to this, I3R minus I4S minus IGG is equal to 0. When the bridge is balanced, IGG is 0. Therefore, I3R is equal to minus I4S equal to 0, or I3R is equal to I4S. So third and fourth becomes seventh and eighth. So dividing this seventh equation with eighth equation, then we get I1P by I3R is equal to I2Q by I4S. Because this I1 is equal to I3 from 5, this gets cancelled, P by R is equal to, since I2 is equal to I4 from 6th, I4 gets cancelled and there is Q by S. Therefore, by cross multiplication we get Q, P by Q is equal to, when R goes to right side, R by S. So when the resistances are in this ratio, that is P by Q is equal to R by S, or P is to Q is equal to R is to S, then the bridge is said to be balanced and IG is equal to 0. So this equation is known as balancing condition of the Wheatstone bridge. Now we shall, basing on this Wheatstone bridge principle, meter bridge is designed to find the specific resistance of the given wire and also resistance of the wire. So meter bridge has a 1 meter length wire, so it is called a meter bridge. Instead of resistance Q and S, there is 1 meter length wire between A and C. That is, this is 1 meter length wire, which is connected between A and C. Therefore, let this be A and C. Here, these are the resistances. This wire is nothing but the resistance. So R and another part S. So when So there are two metallic strips like L shape. A and C. This is also equal to A and C. So between A and C there are two resistances. Between B, so there is another strip. This point is known as B. All these points are known as B. So here unknown resistance is connected across the, let this be unknown resistance X, P. So between A and B there is unknown resistance is connected. This is P or X. We have to determine the unknown resistance R here, P or X. And between B and C there is R, known resistance. This is a known resistance. This is unknown resistance. So the resistance of P by R is equal to Q by S. Already we derived it. So this P by R is equal to Q by S. Known resistance. Let this be P R. This is Q. Yes. So between this B and D, let this be D. Here chalky touching point. Here like pencil in which wire is connected at one tip. So this is known as chalky. Seems to be like this pen, but a wire is connecting inside this. And it is connected to this point B through high resistance key and galvanometer. So this is connected to high resistance to protect the galvanometer, one key and the galvanometer. So this is connected to the jockey. So current Ig is flowing through this. This resistance is capital G. So and battery is connected between the terminals A and C separately. So one battery is connected. This is positive terminal, negative terminal, battery B. This is current I. So the same circuit is arranged in this meter bridge form, where the two resistance lengths Q and S is equal to 1 meter. So when the circuit diagram is connected like this, which is analogs to this Wheatstone bridge. So when the adjusting the resistances R and S are unknown in A B gap, unknown resistance is connecting between A and B gap. Now here, when we touch this jockey from one end to, that is A to C, at one point the galvanometer shows the reading 0. At that point the bridge is said to be balanced, that is the ratio of Q by S is equal to P by R. Therefore from Wheatstone bridge, when the bridge is balanced, according to Wheatstone balancing condition, P by R is equal to, or X by R is equal to, this is length. Generally this wire is made up of nichrome. Each centimeter consists of 2 ohms per centimeter length. Therefore here let this be, as it is total length A to C is 100 centimeters, let this length AD be equal to, AD is equal to L1, and then this S is equal to this resistance length, wire length DC, its resistance BS. This length is equal to 100 minus L1 length, because 100 centimeter total AC is, so L1 centimeter 100 minus L1 centimeter. So this is in the ratio of so for each centimeter 2 ohms. Specific resistance, let it be rho. Therefore L1 into rho ohm centimeter, ohms by nothing but ohms. This is also, X is also in ohms, R is all in ohms. L1 and 100 minus L1 into rho. This is also in ohms. Ohms gets cancelled and the rho gets cancelled. Therefore here we want only X, unknown resistance, X or P. This unknown resistance P is equal to, in this figure, P or X is equal to, from this figure, R into known resistance R into L1 by 100 minus L1. L1 value is obtained from the circuit by pressing the jockey at short pole point D, where the Ig becomes 0. The L1 meter shows the reading 0. Therefore, unknown resistance is calculated by using this formula, and specific resistance R is generally equal to proportional resistance of the conductor is directly proportional to the length and inversely proportional to the area of cross section. By combining these two, R is proportional to L into 1 by A, L by A, or R is equal to specific resistance R or signal rho into L by A. Here we want a specific resistance rho is equal to R into A by L. So by substituting the value of X, here R means resistance of the unknown conductor, unknown resistance here, that is X. Instead of R, here X, we substitute like this. So by using this rho formula for specific resistance, rho is equal to R into A by L. Then in the case of wire which is having uniform cross section area A, and if its radius is R, then A is equal to pi R square. Therefore by substituting this value in this equation, therefore rho is equal to X R P into rho. A, area of cross section, is pi R square by length L, length of the wire. Unknown, this wire length, unknown wire length, P or X length. So that is L. So from this ohm meter or SI system ohm meter. So specific resistance is ohm meter. So from this formula we shall determine the specific resistance of the given wire by using this formula, which is derived from this equation. Rho equal to unknown resistance value into pi R square, its cross section area into its length divided by length L. So here AB is equal to nothing but L, wire length, from tip of this point to tip of this point. So from this equation we shall determine the unknown resistance by using this weighted bridge, and by substituting the value of unknown resistance in this equation, and the unknown resistance length L and unknown resistance cross section area R square. By substituting we shall obtain the value of specific resistance rho RS is equal to X RP into R square by L. So in the next class we shall discuss about the moving coil galvanometer construction working, and the expression for measurement and its application as ammeter and voltmeter, and also about the superconductivity in the next chapter. Thank you.